Today we're going to briefly discuss commuting observables and the idea of commutation in quantum mechanics. So earlier in the course we discussed this experiment that showed that some measurements will destroy information you got from previous measurements. So the one example we looked at was this case where if we prepared a system in a spin up in the z direction state, then measured the x component of the spin, and then remeasured that z component, we saw that by measuring the x component, we sort of destroyed the previous information we had about our system in the z state. And what this, one way of putting this was that these two observables, the spin, the x component of the spin and the z component of the spin, are incompatible. You measure one, you sort of destroyed the information that you had from a previous measurement of the other. So this idea is kind of familiar to us. What we're going to do today is sort of look more formally at this and why that's the case. And we're going to start by defining what we call a commutator, which is the square brackets around the two operators. So let's say we have some two operators, A and B. The commutator is square bracket A comma B, and what it is the operators A and B minus the operator BA acting on some ket. So it's essentially the difference between what you would get if you switched the order of those operations. Much like commutation in math is if two things commute, the order of them doesn't matter. So if operators commute, what that means is their commutator is equal to 0, as in if I operated on B first, then A, if I operated with B first, then A, I would get the same thing as if I had operated with A, then B, right? So what does this have to do with measurement? To think about that, we're going to look at let's look at the eigenvalue equation for one of our operators, say A. A acts on its eigenvector, operator A acting on its eigenvector little a is equal to just some scalar eigenvalue A times that eigenvector again. Now, if A and B, those two operators, commute, then that means this is true. AB minus BA acting on that ket, eigenket A, is equal to 0. So if I expand that out and take those two operators and then bring them to opposite sides, I have AB acting on eigenket A is equal to BA acting on eigenket A. Again, they commute. The order wouldn't matter. But I know from my eigenvalue equation that operator A acting on the eigenket A is just going to give me that scalar A times A. And since that lowercase a, that eigenvalue, is just some scalar, I can bring it out to the other side of operator B, and I'm left with this equation. And if I write that even more explicitly, if I have operator A acting on whatever ket is returned by operator B acting on the eigenket A, I get the scalar A times whatever ket is produced by operator B acting on A. This is an eigenvalue equation. What it's saying is that whatever ket's returned by B operating on A is an eigenvector of A, so that B operating on A is just some scalar multiple, some scalar eigenvalue times that eigenvector. Or put another way, commuting operators share common eigenstates. The eigenstates of B can just be scalar multiples of the eigenstates of A. And we know that just by looking at the math that comes out of if they commute, right? So bringing this back to measurement, let's take some general system with observables A and B. If I prepare the system in one of the eigenstates of A, call it A1, and I've measured that system's now in state A1, then I go ahead and measure in state B. Because they share common eigenvectors, it's not going to change that eigenvector that it's in. It's projected into the same state. So it's still in A1, and then if I measure A again, I still get the same result that I had in my first measurement of A. 100% of the system's still there. Those observables would be compatible. Measuring A would not destroy any of the information I got when I measured B, and vice versa. So that's one of the big takeaways here. If operators commute, they are compatible, and they can both be measured. The measurement of one does not destroy information you have from another, the measurement of the other. If the operators do not commute, the reverse is true. That then they are incompatible observables, and the measurement of one would destroy information about the measurement that you made with the other. So, for example, if we look at the spin 1/2 operators we have in our spin 1/2 system, we have SZ, SY, SX. These are what the matrix representations of those operators are. So if we want to look at the commutation relation between just SX and XY, it looks something like this. Again, just change the order of the two operators and take the difference. If we write that out in the matrix representation, we get this. You get the h bar over 2 from both the two matrix representations out front squared. Then you have Sx times xy minus h bar over 2 all squared sy times sx. If we carry out our matrix algebra with that, we end up with these two matrices, both multiplied by h bar over 2 all squared. We do a bit more math. We get this, where we have 2i and minus 2i on the diagonal. We can factor out that 2i, and we end up with ih bar squared over 2 times 1 and minus 1 along the diagonal of that 2 by 2 matrix. If we look at that, that's actually ih bar times our z operator. And it turns out this is a relationship holds for all our cyclic permutations, you'd call it, of our spin 1/2 operators. The commutator for Sx and Xy is ih bar Sz, and likewise cyclic permutations of those. So Sy, Sz gives us ih bar Sx, and Sz, Sx gives us ih bar Sy. The point being, none of these observables commute. They are all incompatible observables, which we saw when we looked at the results of those Stern-Gerlach measurements. If we measured z component of spin and then the y component of spin, we would have a different result in a subsequent measurement of z. The sequential measurements would destroy information that we achieved from previous measurements of that. Another thing worth noting here that kind of relates to all this is we've mentioned before that operators are diagonal in their own bases. So we typically have been using the z basis, which is a basis that's formed from the eigenvectors of the sz operator. And sz is diagonal in that basis. This is true for all operators. If you make a basis from their eigenvectors, they are going to be diagonal in that basis. So if we take two operators, say A and B, and they are both diagonal in a given basis, like these two matrix representations would be, we can see that A, B, those two operators would form one matrix representation that would look like this. And hopefully it's clear to you that AB and BA would commute in that case. The matrix algebra is pretty straightforward because they're diagonal matrices. There's just a whole bunch of zeros. AB is going to be equivalent to BA. They clearly commute. So if two operators are both diagonal in a given basis, we already know that they share common eigenvectors and they commute. They're compatible observables. So to summarize all of this, what we've done is we've defined a commutator of two operators using this, which is it's written as just square brackets A, B, or whatever two operators you're interested in. And what it is the difference in those two operators acting on something in a different order. So AB minus BA. We know that if two operators have a commutator that's equal to 0, we say that they commute. And what that means is they share common eigenvectors and they're compatible observables. So you can measure one without destroying the other information about the other operator. For our spin operators, we went through this for the one case, but you can do the exact same thing and work it out for the others. The commutation relations are these, where Sx and Xy, the commutator of those are equal to ih bar Sz, and cyclic permutations of that. So just shuffle the letters through. Sy, Sz, the commutator of that is ih bar Sx, and Sz and Sx commutator is equal to ih bar Sy. In the next lecture, we're going to look at this and think of what it means in terms of uncertainty and the uncertainty principle.